hopefully CSIS will get my personnel file to you so that you can have my whole background.
Yes.
Well, I'm really excited to be here and to talk about the hot topic of global warming. So, I didn't even wink. You guys they're a lot smarter than you gave them credit.
Oh, yeah, that's true.
So, you notice how in my title I say the science of global warming. So, I'm a scientist. I'm in the Department of Earth and Ocean Sciences. My background is math and physics. Although when I was in high school, my best subject was English. I don't think I told you that.
No, you didn't.
Yeah, sorry. It's hard to get in that many words. So it's important that even though this topic has big implications in terms of our behavior, in terms of our public policy, in terms of what the government does, the main issues in terms of the understanding if it's really happening or not are scientific. And why that's important, I think, for this discussion is because, well, have you ever heard anybody argue about whether chemistry is the same in Moscow as it is in Vancouver? Like if a chemical reaction is going to take place in Vancouver, that same chemistry is going to unfold in the same way in Moscow, right? This is a kind of fundamental thing in science, is that the things that we study under the large umbrella of science are things that are repeatable, things that are usually based on observation and they're repeatable. So things like emotions or faith or likes and dislikes, those are kind of outside of the realm of science, unless you can somehow make them like observational. Like, for example, you can take statistics on how many people like the color red as their favorite color, then that becomes a scientific question. But in terms of emotions, personal preferences, religion, things like this, that's outside the realm of science. So these kind of questions can't be discussed using scientific methods. But questions like, is the Earth getting warmer? And what are the causes of that? Those are questions that are right in the alleyway of science, so to speak. This is the stuff that science is good at. So before I go into more detail, I'll just give you the outline, which is I'm going to talk about the greenhouse effect. I'm going to go into a lot of the sort of science surrounding global warming and address the questions of what should we do or what can we do. But before I go any further on that, aside from global warming, what science controversies do you ever read about in the newspaper or see on TV?
Evolution.
What's that?
Evolution.
Evolution? Okay, that's a scientific topic, but I wouldn't call it a controversy in a sense, but that's fair. Another one?
The oil sands or the
Oil sands, okay. That's probably like a policy thing. It's probably less about the science. Was there ever
Cloning.
cloning? Okay, so these are all really kind of social things. Can you think of a scientific controversy that didn't have such social implications? Something that's just about the fundamentals of science that was recently in the news.
Paleontology.
Paleontology? Okay, that's kind of a constant.
But the neutrino?
They were disagreeing.
Yeah.
The neutrino. What about the neutrino?
They thought it would go it's going faster than
Then the speed of light. Okay, I can see the top student already in the class. So that's a great example of a scientific controversy. Has nothing to do with how we live our lives. I mean, we're not going to approach the speed of light in our cars. I don't know the way you guys drive, but that's not something that's going to affect our lives tomorrow. But the framework of theoretical physics, and physics is kind of like the sort of underlying building blocks of all of science, rests on this notion that the speed of light is the absolute speed limit in the universe. And when there were these experiments that suggested that maybe that wasn't true, this was big news. And people were talking about this. They were wanting to recreate these experiments. This was like the burning question, right? And there weren't people writing newspaper editorials saying, well, I don't think this is true because of X, Y, or Z. The only people that were really discussing it were the scientists, and they were making these scientific arguments as to why this could be the case, or what the implications were if it was the case. So I'm going to revisit that point later in this talk, but I want you to think about that as like kind of archetypal example, like a standard example you can think. How does science deal with things that shatter its fundamental beliefs? Okay, because this is a prime example. So another example, so the two examples aside from global warming I want you to think about in this talk are this speed of light example, and
Higgs boson.
No, I wasn't going to say nothing so esoteric. You're not.
All right.
You're not the top student in the class.
All right. Oh, I'm sorry.
Nice try.
Okay. I'll leave it to it.
Actually, I'm not looking for a guess. I'm going to tell you that. First I'm going to ask: is there anyone in this room that has never been on an airplane, never taken a flight? Anyone? So everyone here has taken at least one airplane flight. Okay. So that's the other example I want you to think about, because actually there's a lot of uncertainty in modeling the climate. There's no disputing that. There are definitely things we don't understand. But they're the exact same kind of things that we don't understand about flying in a plane, if you can believe that. So climate models, which I'll only touch on a little bit in this talk, they're built on the fundamental physics of the universe. So there are certain principles that we use in physics. One of them is conservation of energy, for example. You can't create energy out of nothing, and you can't destroy energy. Energy, the amount of total energy in a system, is always conserved. So when you think maybe energy is not conserved, well, it's just changed form. So for example, if I push this water bottle along the table, there's this resistive force from the table that ends up dissipating some of the energy in terms of heat. So if I keep doing this for a long enough time, actually my water bottle will get hot. So some of the energy I'm using to push it is changed into a different form, but it's all conserved. The total amount of energy is conserved. So the climate models that scientists use, they use the same kind of principles. So conservation of energy is one of these like hallmark fundamental principles. Well, we use the same kind of physics to figure out how to fly a plane from, say, Vancouver to Toronto. But the hard part about flying is, in terms of writing out equations that can predict everything, is that, what's the most uncomfortable thing when you're flying? What thing do you hate? Turbulence, right. So the thing about turbulence that's difficult is that it's small scale stuff. So when we imagine flying from point A to point B, it's over some vast distance of thousands of kilometers, let's say. But turbulence is has to do with small scale interactions that eventually become large enough that they're felt over a longer distance. So there's this notion. Does anyone have you heard this expression about something about what's that? A star student? What's that, star student?
Butterfly?
Butterfly. What about the butterfly?
Wings? Something about it. The butterfly effect?
Yeah. So what's that all about? The butterfly effect.
Butterfly flaps its wings and Moscow crosses their
Butterfly flaps its wings and you are listening to hurricane.
Yeah, so sort of basically, it's the idea that something small like a butterfly flapping its wings far, far away can somehow have this cascading effect that can be felt eventually downstream in some way. And so ultimately what it's saying is that somehow nature has, even if we know the big picture things that are happening with nature, we can't always predict the effects of these small scale uncertainties. So even though we know, okay, it's going to take approximately 8 hours and 52 minutes to fly from point A to point B, we can't predict in advance when turbulence is going to happen. It's one of these small scale, chaotic or non-deterministic things that we can't predict. And this is why, for example, predicting the weather is so difficult. We can predict the climate. We know, okay, climate essentially is what you expect, and weather is kind of what you get. So we know, okay, January it's going to be rainy and gray in Vancouver day after day after day. There might be one day of sunshine, but we can't predict that in advance, right? But we know more or less what the weather's going to be like in Vancouver. And in a similar sense, that's what we know in terms of climate modeling. So we can predict the big picture things, but there are a lot of small-scale things we're not sure about. And so back to this analogy about flying that I want you to think about as I present the data in my talk. When we're flying and we hit something unexpected like turbulence, what can we do? We can adjust the controls a little bit. We can, oh, there's turbulence coming, there's this pocket of turbulent air, let's fly above it, let's fly around it. Unfortunately, with planet Earth, we can't really, the kind of climate experiment we're doing on planet Earth, we don't really have our hands so easily on the controls. So even though the physics is somehow like flying a plane, the time scale involved in terms of being able to change the inputs so that we can change the output, that happens on a much, much longer time scale. So flying this planet Earth climate plane is a little bit tricky. Okay, so those are the two things I want you to think about during this talk. The plane and how science deals with things like the speed of light. Okay. Any questions so far? Well, there was lots of time for discussion afterwards. Okay, so the thing you probably know about already, this critical thing to life on Earth is this thing called the greenhouse effect. So it's this idea that essentially the sun's rays that come to warm the planet, our atmosphere lets pass these high frequency waves, and as the sun's light warms the planet and the energy gets reflected and kind of re-radiated outwards, our atmosphere traps these lower frequency waves. So in other words, our atmosphere is like a blanket that keeps in heat. So if we didn't have this blanket, if we didn't have this atmosphere, then the Earth would be, I don't know, something like 50 or 60 degrees colder. Like there wouldn't be life on Earth, essentially. So we rely on this greenhouse effect to have this climate that we do. So it's only natural that you think, well, this blanket that we have, if we change somehow the way, here's this diagram that's kind of described what I was just saying. So the sun is the major, it's the only heat source really in planet Earth. So changes to our atmosphere, even small changes, can throw this balance out of whack. So it's a natural question to ask. How important is this balance? And clearly, there has to be some way that one could throw this out of whack. So even more than 100 years ago, scientists were aware that this greenhouse effect is what keeps the planet warm. And even 100 years ago, scientists were aware of the fact that by adding more of these greenhouse gases, we could trap more heat. So this whole global warming debate that you hear about in the media is not something new. So this natural question is, how do we affect things? If the Earth is so big, and if these greenhouse gases we're talking about things in the parts per million or parts per billion, a lot of people might say, well, how is it even possible to affect the planet? But it's the key is this balance. It's like, but by adding more, eventually, if you keep adding more greenhouse gases, you're going to trap more heat. So the only debate, so there's really not, as I'll show you in this talk, there's really not that much debate in terms of the science of climate change anymore. And the only debate that there has been over the past, say, 30 years has been just how much of an effect do humans have. So there's no question that this greenhouse effect is the reality and that greenhouse gases trap heat. The only question is how much of an effect is due to humans. So the main greenhouse gases that we worry about, water vapor, which kind of doesn't really last too long in the atmosphere. Methane, so you think the stereotypical example of methane is like cow dung, I guess. And carbon dioxide. So carbon dioxide is the one that probably you hear about the most. All three of these have sort of greenhouse gas properties, so they all act like a kind of blanket to trap heat. Some quick carbon facts are, these are things you probably already know, that mainly burning fossil fuels is the major driver to increased greenhouse gases, and that since the Industrial Revolution, we've really ramped up the amount of greenhouse gases that we've put into the atmosphere. I put these facts here mainly because when we discuss what to do about this problem, part of the issue is that countries kind of fight over whose fault is it, and how much does the past matter in terms of making policies about the future. Another critical aspect of the I guess the balance of greenhouse gases on the planet is deforestation, and it's kind of a triply bad thing because when we burn trees from forests, it releases carbon to the atmosphere. When we remove these trees, then they're no longer there to absorb the CO2. And often, as in this case here with the Amazon, cattle ranches are, I guess, 3/5 of the deforestation in the Amazon are for cattle ranchers, and they're another producer of greenhouse gases. And in fact, since I'm on this topic of deforestation, often when people talk about offsetting their carbon, if you ever go on a flight and they say, would you like to offset the carbon emissions from your flight? One of the ways people suggest that you offset your carbon emissions is by contributing to some fund that plants trees. But it actually doesn't matter that much to do this in the northern hemisphere where we live. The best place, if you want to have some kind of impact on the climate, is the tropical rainforests. So if you were to offset your carbon emissions, you should do so by taking that expensive flight to the tropics and planting some trees, or paying a company that's already doing that for you. So another important fact about this debate is that CO2 is definitely increasing. So there's this famous data set from Keeling called the Keeling curve. And what Keeling essentially did was he took CO2 samples at this observatory in Hawaii over, this data set here is like since 1958. And there's a really clear CO2 level rise. So in terms of measurements that we've taken to sort of validate what's happening with CO2 increase, this is one of the prime data sets. There are also, you might hear about ice cores that have, you can get CO2 information from ice cores that actually stretch back about 150,000 years. There's another data set that we use, but this is probably, in terms of the period in the Industrial Revolution, one of the sort of more famous data sets. And I have a couple pictures of evidence of warming. So you can see evidence of warming all over the place. I'm sure if you Google this, even maybe in your own lifetimes, you've seen the effects of changing climate. So these kind of, so here's Glacier National Park in Montana, and then Larsen B ice shelf collapse. So this is the kind of stuff I study. This giant ice shelf that just disappeared. It's the size of a fairly large U.S. state. I mean, it's large. It's not one of the larger U.S. states, but it's a fairly large chunk of real estate. And why this example is so important is that ice shelves, sort of floating ice tongues, they are effectively holding back the ice that sits on top of Antarctica. So in terms of sea level rise in the future, the ice that's floating, so like icebergs and ice tongues, they don't contribute to sea level rise at all. In the same way that if you're drinking a glass of water that has an ice cube in it, when the ice cube melts, the water level stays the same, right? But what this ice tongue, this ice shelf does is it's effectively like a valve that can increase the flow of the land-based ice into the ocean. So this shelf is kind of like holding back this ice, and when it breaks off, the ice on the land will flow out to the ocean more rapidly. So as these shelves break off sooner and disappear, it increases the flow of land-based ice, which increases the sea level rise. So these are nice pictures, you know. I mean, they're very showing very clear evidence of change. Yeah.
When you say rapidly, how long the mass movement? Like,
Well, good news for you, and well, for all of us, not just you. Unless you're in the marine, like shipbuilding industry, in which case maybe it's bad news. I'm not sure. Well, okay. So first, the scary thing is that there's enough ice. There's enough land-based ice in Antarctica to raise sea levels by about 60 meters. So if all the 60, So if all the ice in Antarctica were to suddenly go into the ocean, 60 meters.
We'd be underwater.
Yeah, I'm a really bad swimmer, by the way. But in terms of timescales, the good news is that, okay, while we don't really understand this stuff very much yet, so there's a lot of uncertainty in this, but the timescales for this to happen are really long. Like, it would be thousands of years for that to happen. So there's not really a risk that Vancouver's going to be underwater tomorrow. So that's one thing that I want to make clear is that sea level rise, our best guess right now, and this is only a guess, is we're looking at maybe a meter in our lifetimes. So that seems like not very much. If you live in Bangladesh, that's a problem, or if you live in the Netherlands, that's a problem. But or in Delta, maybe that's a problem, I guess.
Richmond.
Yeah, Richmond. Yeah, we don't need an airport. What are you worried about? Okay, so one thing I want to make clear is that that's not anybody that tells you we're all going to be underwater. That's not really. It's an exaggeration. So another thing that I want to point out about these pictures. These are nice pictures, right? But just like the weather is really variable, so the Earth's climate is really variable, and even if the average temperature is increasing and continues to increase all over the globe, there are regions on the planet where the temperature is not increasing. So there's a recent study, for example, of glaciers in the Himalayas. There's a section of these glaciers that's experiencing growth. So there are some glaciers in the Himalayas, like most of them are shrinking, but there are some that are growing. And that's not at all surprising, right? I mean, when you look at the whole planet Earth, there are going to be places that warm and places that cool with any kind of changing climate, right? So whenever someone shows you like one or two pictures to like prove the point, that's not a proof at all. I just happen to show you pictures that fit my argument, right? So that's, keep that in mind. Don't be fooled by this dramatic picture that I just showed you. What's much more important is to look at all of the data at once, right?
James?
Yep.
If you had a contest with somebody who's got the other pictures of ice masses growing,
Yeah.
And he ran and got all of his pictures, and you ran and got all of your pictures.
I have more
You're saying
pictures.
that you'd have more pictures.
Yeah, a lot
Yeah.
more pictures.
Yeah.
Yeah.
Okay.
But that's not like that's not a particularly like scientific way of doing things.
Okay.
So and I'll get into this in a bit. Okay, so now if you accept what I'm saying so far, okay, here's another example that's highly cited and a little bit dangerous. People like to say, "Oh, Hurricane Katrina, global warming. See, I told you. All these people died in Hurricane Katrina. Global warming is a reality. We have to do something about it." Well, you can't. The problem with that argument is that you can't blame one event on global warming. What you can say is that in a warming climate, then extreme weather events are more likely. That's all you can really say. So stronger storms, more rainfall in some areas, more droughts in other areas, just depending on things like the trade winds. So for example, Kilimanjaro, so the highest mountain in Africa, has glaciers, rapidly retreating glaciers on the top of Kilimanjaro. Kilimanjaro, apparently, I haven't done it, but apparently it's an easy hike. So if you ever, the highest mountain in the entire continent. So if you ever happen to find yourself on the Kenya-Tanzania border, apparently, easy hike, you can see glaciers. But only if you do it in the next 20 years or so, because they're shrinking so quickly. However, here's the surprising thing about Kilimanjaro. The shrinking glaciers in Kilimanjaro have nothing, or almost nothing, to do with global warming. It's a change in the atmospheric circulation. So glaciers need precipitation, in other words, snow, to grow, right? And it's just happened so that over the past, I think, 50 or 60 years, the circulation patterns in that region have changed so that there's just less snow falling there. So the temperature has increased moderately, but that's not the main reason for the mass loss. It's just that it's just not snowing as much. So if people say, oh, well, Kilimanjaro is shrinking, climate change, I told you. Well, it's not anthropogenic. It's not like human caused. It's just a change in the circulation patterns of the Earth. So anyway, back to this example, Katrina. It's not, question?
So now where is it snowing more?
Where is it snowing more?
Is it in the Himalayas?
Whistler is snowing more. Yeah, it's close by if you've ever checked that.
Is it snowing more in Himalayas? Like you mentioned before? It's due to the...
Well, so the Kilimanjaro case, that's East Africa. And so I think what it means is that there are regions nearby that mountain range that are getting more rain. So maybe a little bit north, I'm not sure. And I mean, of course, there are going to be places in, say, the Himalayas that are going to have more snow than they used to or less snow than they used to. I mean, it just, circulation patterns change.
So is the cause of that? Like, it just shifted from there to there?
Yeah, I don't think you can really say it shifted from Kilimanjaro to the Himalayas because they're so vastly separated. But we don't have the globe in here, huh?
Oh, no, with the world over there.
To get the world.
A no globe.
Yeah, that's okay. Anyway, you know what the world looks like. I mean, so you can get these, if you look up things like the trade winds, or in the ocean they have this thing called the what do they call it, the global ocean conveyor belt. You can look up these like currents, these kind of main trends that weather patterns have, weather circulation patterns have. And in some regions, those will flip depending on the season. And it's just kind of a complicated sort of mathematical problem to, predict how these things are going to change.
Well, and it needn't necessarily snow more somewhere else just because it's snowing less.
Yeah, that's true.
There's nothing that follows.
Yeah, but in any case, you should expect that the climate is variable. And anytime someone gives you like a one-of example, you should always be suspicious, right? Because if we're talking about the global temperature on average is increasing, then I can give you 100 examples on one side or the other, and that doesn't really prove anything, right? So in terms of this Katrina example, so I think in the Al Gore movie he kind of focuses on this a lot, and I think that's a little bit unfair because it was an unfortunate hurricane that had a lot of loss of life and damage to property, but it's not something you could link unequivocally to global warming. So anytime somebody does that in any kind of scientific debate, be suspicious. Okay, so here's from, I got this from the NASA website the other night. So this is the typical kind of data set that people use to look at whether or not the Earth's temperature is increasing. So what they do in this data set is they have a whole bunch of stations all over the Earth. So they have weather stations, like meteorological stations. Some of these might be from weather balloons. I think they're mostly stationary stations, like weather towers. And for each year, they take an average of all of these temperatures. Okay, so the black curve is the annual mean. So what that means is that for each year, each basically dot on this is an average for that year. But one thing that you'll learn if you ever deal with a lot of data sets is that there can be a lot of strange noise in the data. And so to see a trend, it's often better to take a slightly longer, what's called a running average or a running mean. So the red line, which you can see is kind of a bit smoother, it's a 5-year running mean. So what that means is that at any given year, instead of using the data for that year, it takes 2.5 years on either side and makes an average. So what that will do is it will smooth out the really big peaks and the really big troughs, so to speak. And you'll get a better idea of the long-term trend without the variability. So you can do these like different size means, but 5 years seems like a good amount for this data set. But in any case, whether you're looking at the annual mean or the 5-year running mean, you can see there's a clear upward trend. Question? Uh-oh, we have to evacuate.
How about alarms?
Doesn't the temperature decline from 1940 to 1980 during the most peak industrial activity?
Well, so
That's interesting.
so there are definitely places in the data where you can see, if you take a short enough window, where you can see a lot of funny things. Okay, so it's true. There doesn't seem to be as much. This looks fairly constant. It's true, but it's.
Isn't it more of a time period from 1980 to 2000?
Well, again, it really depends on how big or small a window you want to take. Because, for example, you could say, oh, well, look at this period from, I don't know what that is. Let's say it's 1983 to, or maybe it's like 89 to 92 or something. Wow, look at that huge drop. What's happening on planet Earth? Global cooling, right? And you could say similar things like here or here. Like there are so many places where if you look in a small enough window, you can kind of see whatever you want, right? So this is a critical question: is what do you do when you have a data set, what we call a time series, because it's data that changes with time. What's the best way to view that data? And it depends on what question you're trying to answer. So if you're trying to answer a question about something since, say, the Industrial Revolution, then you probably want to go as far back as possible. If you want to know links between CO2 and temperature, like for 100,000 years, obviously this, you wouldn't care about a fluctuation in 5 or 20 years, right? So that's a really good question. But I guess my answer to that would be, well, there are a lot of complicated dynamics in the climate that we don't totally understand, much like we don't understand, like we can't predict turbulence on a flight from LA to Vancouver. And one common example of the kind of weird behavior in the climate that sort of skews the results a little bit sometimes is a lot of people say, well, there hasn't actually been any warming since 1998, because 1998 was apparently the warmest year on record, right? And maybe some of the data suggests that maybe 2010, depending on who you ask, was as warm or warmer than 1998. But let's say they were tied, or let's say that 1998 was fractionally ahead. Somebody might tell you, well, hasn't increased. Our warmest year on record was 98. That was a while ago. So global warming has stalled. But that's not okay. So it's hard to say that because we're talking about a really small chunk of time on this line, right? So it's hard to talk about any kind of trend just from a couple of years, just from a decade. Okay, first thing. Second thing is 1998 was a special year in that it was an El Nino year. So because it was an El Nino year, it turned out that kind of artificially boosted the mean temperature. So there are a lot of these different oscillations. So there's the El Nino Southern Oscillation. There's the Pacific Decadal Oscillation. There's something called the Madden-Julian Oscillation. There are all of these things that happen in the circulation of the planet, both the oceans and the atmosphere, where you can have things like constructive and destructive interference. Do you know about that from physics? Does anyone know? Who doesn't know what that means? Okay, so the way it works is imagine that you have a wave. You have two waves that meet, and they meet in such a way that their peaks coincide. So this other wave meets here too. So these peaks somehow add so that they constructively interfere. So, sorry, the diagram's not very good. I should have made a picture of that. But basically, it's the idea that you can have waves that are just in sync in the right way, so that they constructively add up and they double everything. Or you can have waves that are just out of sync, so that they totally cancel each other out. So if they cancel each other out, we call it destructive interference. And if they kind of superimpose on top of each other and add, we call that constructive. So there are all of these oscillatory effects that have to do with the circulation in the planet, where you see these effects recurring over some kind of periodic cycle. And so 1998 was one of those El Nino Southern Oscillation years. So that's another reason why 98 is believed to be kind of artificially warmer than the years around it. But in any case, since 98, well, I think it's something like the 10 hottest years on record have all occurred in the last 15 years or something like that. So even if 98 was the hottest year, even if there isn't a hotter year since, almost all the other hot years have been around that time. So just by looking at that small chunk of time, we can't really talk about like a cooling. But even so, even if somebody says to you, oh, well, it hasn't warmed since 98, which isn't totally true, the sort of fundamentals are kind of unchallenged in that greenhouse gases trap heat. And the more greenhouse gases we emit, the more heat we're going to trap. It's really just a question of how fast that's going to happen and how over what time period the temperature's going to rise. But yeah, so anyway, the short answer to your question is, yep, that looks like a slight downward trend. And this is an upward trend. And overall, it's an upward trend. It just really depends on the time scale that you look at. Right? Yeah, so, oh, go ahead.
Question, you mentioned glacial analysis for finding out higher CO2 in the atmosphere.
Mm-hmm.
How accurate is that? Say if I wanted to find out how the CO2 atmosphere was in the 1700s, would I be able to accurately?
Yeah, so I guess the idea is that you take this ice core. So the ice has basically, it's kind of like tree rings in trees in some sense, right? So it's this kind of snapshot. Well, I guess in some sense a proxy, what we call. So it's not. Okay, so what you can find out from an ice core is, so you have all of these sort of layers of ice from different periods, and you can see the amount of CO2 trapped in that ice. And so you can make some inference about what was the atmospheric level of CO2 when that ice was exposed to the atmosphere before it was kind of covered over by another layer of ice. And so you can say, but by comparing measured value to something known, so for example, CO2 measurements in the 1950s compared with, say, this CO2 from an ice core that we think is from the 1950s, we can calibrate it, and then we can try to go, once we've calibrated it to something we know, we can go backwards. So when you do that, there's always going to be some uncertainty, right? Because of the measurements you're making and because of the way you're kind of evaluating that data, sort of extrapolating it backwards.
Does the data have to be taken from the same area for it to be valid?
I don't know if it has to be from the same. I don't really deal with ice cores as my expertise, so I'm a bit cautious to answer that question. But I think there are ways of kind of validating, I think there are ways to compare ice cores from different regions. I know, for example, they have ice cores in Greenland and in Antarctica. I think the Antarctica ones stretch back much further than the Greenland ones. But they're able to kind of compare these CO2 records and then link them to temperature records that they have from other sources.
Is there an observed rise in the CO2 levels in the years?
Yes. So I don't know if I have I think I have a picture of that coming up. Oh, yeah, sort of here. Okay. So this sort of are we responsible picture. I think, okay, so black is CO2, red is average Earth temperature, and blue is sea level. Okay, so here's present, and this is 50,000, 100,000, 150,000, I guess 200,000 years ago. So here's kind of a good sort of contrast to the plot that you were asking a question about before, because now this time scale is gigantic, right? This is like 200,000 years. So things like, we know, oh, is that a slight rise in that 50-year region? We can't see that on this plot at all. But we can see that in some really kind of sort of gross, sort of first guess way, these curves all kind of follow each other, which isn't so surprising because we know greenhouse gases are going to trap heat. So we would expect if there's more CO2, it will trap more heat. The Earth should be warmer, right? And also, a warmer Earth means at least sometime down the road, a sea level rise because more ice will melt. Question?
You know how you said before a warmer Earth means the ocean expands in volume,
Mm-hmm.
and oceans, when they're warmer, they do the water vapor that arises from the oceans. Isn't that a correlation to the temperature as well? Because water vapor is a greenhouse gas, and there's more water vapor in the atmosphere than CO2.
Yeah. So I think that question has been studied a lot, and that's not something that I'm incredibly knowledgeable about. But I know that from what I've read, I think that stuff kind of all. If I word this right, this could be a clever pun, but I'm not going to risk it. But I think all that kind of water vapor kind of comes out in the wash. It kind of gets. Essentially, yeah, it's a more powerful greenhouse gas, but it also doesn't have the lifetime in the atmosphere. Like it's a really short. Like you get a certain concentration of water vapor. Eventually, it builds into these hot towers of clouds in the tropics that eventually burst into a hurricane. So there's not a lot of there's a fast turnaround for that kind of greenhouse gas. So all the studies that I've seen, and I'm sure there are thousands of papers in this in the literature. All of the studies that I've seen suggest that that's not because of the fast turnaround. It will change, for example, the cycles of precipitation. And it will change kind of how much it rains, where it rains, how likely is it to have an extreme weather event like a huge storm. But it doesn't really change that much in terms of heat trapping of that sort of greenhouse gas effect. Although an interesting question about clouds, water vapor, has to do with albedo. Do you guys know what the albedo is? What's albedo?
How much reflection an object has?
Yeah, that's right. So, for example, snow and ice have really high albedo. I mean, they just reflect light back into the atmosphere. But black carbon, which is basically like soot. It's like soot. Soot. Yeah. I grew up in the Maritimes, so I sometimes mispronounce words a little bit. So black carbon or soot, that reduces the albedo. So if snow or ice gets kind of blackened, then it's going to want to absorb light, and it's going to actually increase the warming effect. So these are things that have really been studied quite a bit also. So as we lose snow and ice cover, that's a feedback that's going to make the Earth want to warm up even more. But the reason I brought it up with what you said is because another sort of active research area among the people who do cloud physics is if there's more water vapor, if there are more storm clouds, what's the albedo of a cloud, and how do the effects of changing sort of reflection from cloud cover changing, how does that change the planet? And so those are kind of actively investigated questions, which I don't know the answers necessarily to. Okay, so a lot of people make these fancy climate models, and they try to predict what's going to happen in the future. So the problem is, as mentioned before, is that we don't have the controls to this, climate airplane that we're on. And so all we can do is make a model that's based on sound physics and compare it to what's happened in the past. So we can make a model and we can give it all the inputs of what was the climate like in 1905, what was the climate like in 1940, and we can try to make models that predict the weather we've already seen. But we can't so easily test those models into the future. It's on some level, it's some kind of a guess. We hope that if we can predict the past, then we hope that's a reasonable indication that we can sort of predict the future, right? So these climate predictions are there's a lot of uncertainty in them. But even so, people make these different models and they try to predict. They put different greenhouse gas emissions and they look at what the sort of warming results are for those models. And as you can see, by 2100, hopefully we'll all live to see the year 2100, right?
Absolutely.
Good. We went for sushi, very healthy if you want to live forever. It's a really good diet. So you can see there's a really wide range of predictions. So some models predict only half a degree of warming by the year 2100, and some models are predicting up to 4 degrees. Generally, these models underpredict things. Why do you think they underpredict things? Any guess?
Conservatives.
Yeah. Stephen Harper's behind. No, not that conservative.
Oh, okay.
They assume that the rate at which we're increasing stays constant, not doesn't like the rate at which something increases.
Not necessarily. I mean, you can see that these different scenarios have different sort of inputs. It actually it has more to do with how we can kind of calibrate them, how we know they're good. The only way we can calibrate them really is by looking at the past, and by doing that, we're kind of we know how the Earth has behaved in the past, but we're pushing the envelope in terms of parameters that we understand. So we know how the Earth behaves with a certain amount of CO2. We're adding a lot more. So we're going to push the Earth to a point that's outside of the realm of our previous knowledge. But our models will tend to make things that look a little bit more like what we already have. So models tend to be conservative. Like there could be some feedbacks that we don't get quite right, and we could actually be a lot warmer than this. We don't really know. Question?
James, I've been talking to the kids all week about this, and as you know, I primed them to ask some questions, and I've been hearing them. What I haven't heard yet, though, is that if you look at and you have given us some historic, like 200,000 year schemes, there has been reference in our work towards this meeting today about natural ups and downs of the effect of the sun,
right?
Irrespective of human existence, never mind contribution. Could you comment on that?
Yeah, so the sun is obviously, it's the big heat source, right? So one of the first questions, actually, what's my next, okay. So one of the things that I wanted to mention in a couple of slides from now is, okay, so there are a few major sort of questions that people like to ask about the science of anthropogenic global warming. So one is, how do we know it's not the sun? Because we're, these puny little creatures on the planet that, seem to we have trouble getting our own lives to do what we want. How could we affect something so vast like the planet? So the sun seems like it's a more natural cause. Also, another thing that people look at are this heat island effect. I don't know if anyone's read about that. Heat island. It's not. I'm not talking about Hawaii.
No.
I know what you're thinking. What's that? What's that? No. You look confident for a second.
I don't want to take away your speech.
No. It's not. You're in discussion. It's your turn.
Oh wow, people are staring at me. Now I'm feeling quite.
No, you're
Be more shy.
You said something urban something.
Yeah, like with urbanization.
Yeah, so it's linked to urbanization. So there's one theory that that a lot of the places where we collect data for temperatures, a lot of these temperature stations, they're either at airports or in urban centers, which are both expected to be like hotter than average. And so some people were saying, well, this heat island effect, if you have all of your weather stations in hot places, maybe you're seeing more. Well, how do you know you're not just picking stations that are the ones that give you the results you want, right? So there is a, I'll just kind of fast forward here. These guys at Berkeley have a catchy acronym, BEST. So Berkeley Earth Surface Temperature. So the story of these guys is that there is some interest in the U.S. I think it was the Koch brothers. There's like I think they were tobacco people or maybe they're oil people. I can't remember. But they basically
Koch?
yeah.
Koch.
Koch? Is that's the kosher way of saying it?
Yeah.
So I think the Germans would say Koch. The Koch brothers, but the Americans, you know. In any case, they decided, okay, we doubt climate change. We don't want it to be true. All the science so far we've seen suggests that it is. Let's pay some impartial scientists to look into all of these issues. So they got some money together, lots of money, and they got this crack team of like the top people. So Richard Mueller is the head of it. He's a physicist at Berkeley. I think they had 6 or 7 physicists, a statistician. One of the people on their team was a Nobel Prize winner in physics. They're like top scientists who are not climate scientists. And so they wanted to look at heat island effect. They wanted to look at things like solar variability. And this is what he said. He said, you know, we're bringing the spirit of science back to a subject that has become too argumentative and too contentious. We're an independent, non-political, non-partisan group. We will gather the data, do the analysis, present the results, and we'll make it all available. There will be no spin whatever we find. We're doing this because it is the most important project in the world today. Nothing else comes close. So they released the results last fall. And okay, so here's just a little graph of kind of some of the things they were looking at. So you know the sun's energy output, changes in land. So aerosols, urban pollution, and land use changes have a sort of net cooling effect. But you know, heat trapping emissions we believe have a warming effect. So these are the kind of different things they were looking at in addition to like bias and possible bias in the data. What they found is that the heat island effect and poor station quality didn't really bias the results. All the data they found basically matched the results of all the other main scientific groups like NASA and the Hadley Center in the UK. So a third of the sites were found to be cooling on average, but 2/3 were found to be warming. And we're talking about global mean temperatures. Obviously, there's lots of variability in the data. There are places that have been getting cooler and cooler each year. I mean, there's so many corners of the world that have sort of weird, different kind of effects going on that, sure, not every place is going to be warming. But on average, 2/3 of these sites over the past 70 years showed clear warming. So this is just one example of sort of several prominent reviews of the science that have been done in the past 10 years. Another thing they found is there's one particular kind of oscillation that seems to be important, that somehow the temperature increase in the global warming cycle is tightly tied to this multi-decadal oscillation in the Atlantic Ocean. Nobody really knows why, but that's just what they found from the data. So that's an example. Impartial scientists that looked at the data and they couldn't really find anything wrong with it. And just think back to that example I gave it in the beginning, the speed of light, the neutrino, as our star student pointed out. If I was able to show a reasonable scientific argument that suggests that anthropogenic global warming was not happening, that would make my career. If I could publish a result, even if the result was not like totally perfect, if it even suggested that, you know, some of the basic science we have is wrong, man, I could publish it in the best journal, instant professor, I could live the good life. And that's the thing about sort of the nature of science, is that if you have a really good scientifically sound argument and it matches with the data and you can publish this, then, you know, people want to see that.
The same answer you said to the question, if you did this and you get money, isn't that a motive, and isn't that confirmation bias towards your information you're trying to find?
Okay.
So like all the scientists who do try to look for the fact that it is anthropogenic, then don't they look for it because they're getting funded by bigger companies?
But actually, that's an interesting point that lots of people bring up, but it should actually have the opposite effect, because no one's going to fund me to prove what the scientists already believe, because, like, you know, all the data suggests that it's already true. So if I wanted to be famous, let's say, you know, I'm magic and I can make the universe do whatever I want. I want to create a result that no one's ever seen before. That's how I get funding.
James, the language that Rita and others would understand in this course is that the reigning paradigm suggests global warming. The anomalies that you might find that would produce a new paradigm would make him rich.
Yeah.
So if there is a motive for self-centered skewing of information, it would be to replace the current paradigm, which is, in the world of science, that the world is getting warmer.
Yeah.
So that's what he's talking about.
Yeah, and so on that, and another critical question sort of that I touched on at the beginning is how science is communicated. And so I mentioned that people don't fight about, scientific truths in newspaper editorials or on TV talk shows. They do it in these journal publications. And so I'm just going to explain quickly how the peer review process works. So let's say that, what's your name?
Read it. H-R-I-D-A-Y.
The H is silent.
Okay.
Friday.
Okay. Friday. Okay. So let's say we write a paper together. Okay. And let's say we have a brand new theory that the temperature fluctuations in this classroom are actually responsible for global warming. And we can match it to all the data. It's something about this magical part of White Rock or South Surrey, whatever you call this part of the world.
Call it White.
And we can publish this in some journal. What will happen is we'll write up the paper, and we'll submit it to the best journal we can, which is probably Nature. That's like everyone wants to publish in Nature. The editor will look at the paper, and probably he'll first think it's garbage, and then he'll look and he'll see how brilliant our science is, and he'll say, okay, I'm not an expert in this. What I'm going to do is I'm going to submit this to some reviewers. So reviewers who are experts in the stuff that we're talking about, they will look at the paper, they will try to find holes in the argument, and then they will make a whole bunch of recommendations, and it'll be anonymous. So the editor will... Are we
We're so good.
Okay, I'll try to be fast. Okay, so the editor will say, okay, I got these results. Listen, guys, your anonymous reviewers said, and he'll give us the results. And the results will be something like, these 6 arguments are bad, your data was, unclear here, I don't believe this conclusion, whatever. And then they'll say something like, if you fix these are just small changes, and if you fix these little changes that I'm suggesting, if you deal with these issues, then we publish it. Or he might say, no, your paper's just total garbage. But it's totally anonymous, right? And so once that is checked and then we've fixed it, if we fixed it well enough, then it will be published in this journal. So this is a kind of typical peer review process where you can only publish if you, as Isaac Newton said, if I have seen further than others, it is because
They're on somebody's shoulders.
Stand on the shoulders of giants.
On the
You're on the shoulder of giants.
Yes. So in the way the peer review process works is that essentially the experts check to see if you've kind of followed the sort of scientific standards and if the shoulders that you're standing on are solid. Let me just say that a lot of different theories have been investigated, and this stuff is like been published, for decades in the scientific literature. All these things about solar variability, changes in albedo, heat island effects, and for sure there are lots of uncertainties. For sure there are things that we don't totally get, but there's no other explanation for these warming effects. So solar variability, so there are 2 types of solar variability that get studied. One is that, changes in solar intensity are the things that can cause ice ages. But that happens over really long time scales. So over the short time scale that we're looking at, like the past 150 years, there really isn't so much solar variability. There's also an argument about sunspots. There's this 11-year cycle for sunspots. But one thing that you can really easily do with time series data is you can do this spectral analysis, basically like frequency analysis. So if anyone who edits music, does anyone do any music editing and stuff? Okay, so there's a lot of stuff you can do with, that was a good dance. There's a lot of stuff you can do with signal processing where you can very easily pick out certain frequencies. So in a time series data, like the kind of like temperature CO2 data that we have, it's really easy to go into what's called the frequency spectrum and just look for things on an 11-year cycle. And when you do that, there's no 11-year cycle in the data. So there's no real link to something like sunspots. So really, I mean, you can't really find. You can find almost no credible scientists that will argue the contrary of this.
If there's no debate in the scientific community, which I understand, why is there such a widespread controversy in public opinion? Like in the U.S., it was something like 20% of people didn't, like only 20% believed that this was.
Yeah. Well, I mean, I guess the problem is that it's annoying to have to deal with this reality. You know, the science tells us something, but changing it requires not necessarily incredibly drastic lifestyle changes, but some lifestyle changes. And if this doesn't fit in with your worldview, if you work for an oil company, or if you have certain beliefs that sort of clash with this, then it's just going to be a lot easier for you to point to whatever uncertainties you can.
There's a phrase that I'll remind James of, that we all need to remember when we live next door to the United States. It's called American exceptionalism. And really, it's profound. It really is profound. You really need to understand this, guys, because the American culture, as a general culture, really does believe that they can do no wrong. That the things they're doing, such as CO2 production, cannot possibly be causing any harm because it's being done by Americans. It's a deeply felt belief in the purpose of the foundation of America 200 years ago. That this is an exceptional, extraordinary place which cannot do wrong. I don't think you understand, as young people and as Canadians, and not only that, but people all over the globe, I don't think you can't quite get the impact of that deep cultural belief in America captured by the phrase American exceptionalism. I had to jump in there because I know about that stuff, and James is full of all the physics. I'm full of all the BS surrounding culture, so.
But I think that we have the same attitude a little bit towards the tar sands. I mean, that's like seen to, if you go to Calgary, all the tall buildings have the names of oil companies. I was visiting a friend of mine who goes to the University of Calgary, and even the buildings on the campus are like, the Suncor Library or the whatever. They're all, it's an oil city. It's been built on oil. And so clearly they don't want to, the implications in terms of decisions we have to make in the future are sort of bad for that business.
So big business is influencing people.
Yeah, sure.
Two questions, sort of. What do you think about Canada leaving the Kyoto Accord? And also, there's a whole idea how with the whole recycling movement that personal changes normally do anything. If a person starts recycling, it's not going to do anything. It's the corporations that are causing the harm. To what extent are the corporations the ones most responsible for the harms in the cases of CO2 emissions?
Yeah. So, okay. So those are really good questions because those cut to the essential questions that you might have, which are, what can we do about it as individuals, and who kind of bears the responsibility in terms of governments and big businesses. So one of the criticisms of the Kyoto Accord is that even if we fulfilled our Kyoto obligations, even if we had stuck to it, and if the Americans had actually signed on, it wouldn't have had that much effect. And it's true, actually, in a sense that Kyoto, it was too difficult right now for countries to achieve, yet it also wasn't strong enough, it doesn't kind of do enough, which sounds really depressing, doesn't it? And you ask, well, what about recycling, and what about being a good citizen, and where does the weight of responsibility fall in terms of corporations? So before I answer that, how many of you here have gone into a coffee shop and have been able to buy fair trade organic coffee? It's easy. It's easy if you look for it. It's everywhere. I think every coffee shop has fair trade organic coffee now. But it didn't used to be that way. In fact, maybe 15 or 20 years ago, it was like, you were some crazy hippie if you tried to say, I'm not going to drink that coffee. That's, what about the people working on the coffee plantation? What about, that's not ethical. So why did that change? Well, it changed because enough of those crazy hippies convinced their friends to have the same crazy hippie viewpoint to try to stop exploiting people. So I think that when you have a complex fluorescent light bulb, or when you you ride your bike instead of driving or something, you think that's a small change. And it is, and in terms of like the bottom line of greenhouse gas emissions, it seems like a small change, and that the faceless corporations are, we can't stop them. But I think that as long as we are aware of the choices we make, and we, in our own way, kind of ask for change, then we can't really say at what point is the critical mass going to be large enough where all of a sudden these companies have to listen. So for example, so when I was in high school, Nike made all their sneakers in sweatshop conditions, and they didn't care. And they would have like 10-year-olds in East Asia making these sneakers for peanuts, and then they would sponsor basketball courts to be built in ghettos because that's where future NBA stars would be, and they were doing this really bad, like optically it was really bad, right? But eventually people got so upset with Nike that finally one day Nike said, that's it, we're going to change. And now, in terms of sort of ethical labor practices, believe it or not, Nike's the leader. They are the best company in terms of manufacturing in Asia. They set the ethical standards. And that's because people eventually got too pissed off and they kind of forced Nike to change. So I think that even though it seems like it's difficult now and all of the projections sound kind of negative, I think that we can make a difference. One thing that I'll point out is that, okay, procrastination is decision.
It's doing nothing.
So when we say, oh, why is there, you think you asked, like, why is there seem to be all this debate?
Yeah, like
Well,
there's disconnect between like the scientific community,
Yeah.
you mentioned has like almost complete consensus, but there's this huge split in terms of public opinion.
Yeah, well, you have to ask, like, in whose interest is that? If we procrastinate, we're choosing to do nothing. So the people that support that are usually the people that have something to gain from it. So as long as we remain kind of divided on that issue, then it's easier for the interests that like can make money off of, say, business as usual. Those interests will prosper. So we don't want to keep procrastinating. But it's not like we need some miracle new technologies. All we have to actually do is things like investing in alternative energy sources. So I don't have, one contentious thing maybe is nuclear power, and that's like an issue that I won't want to bring up. But I mean, that's a possible solution in terms of maybe it's better than coal in terms of CO2 emissions. But if we put enough resources into these alternative energy sources, then they become cheaper because more people kind of buy into them, in terms of like economy of scale. And there are lots of ways to motivate ourselves, and even all these little things, as I say, if you can sort of change yourself and those around you, you can eventually, I think, hopefully change the world. Were you going to say something?
Yeah, go ahead, please, Brady.
You know how you're talking about how there's all this funding for these green technologies, and then that's exactly why the scientists would continue to say that it is man-made, because they're getting all this funding from government subsidies, and they're investing all their research into new energy technologies because people are funding them.
But those aren't the people that, I think the people that do these kind of technologies, these are like these are like engineers, these are like entrepreneurs, these are businessmen. These aren't the people, these aren't the scientists that are examining the data. Like I'm a glaciologist. I don't build solar panels, I don't build electric cars. Like I don't have anything to gain from this industry.
But the entrepreneurs themselves, solar panels and wind power is way more expensive, and
right now
it's not efficient at all. Well, right now it's not efficient, and for them it's not economically viable for them to invest their time and money into this, because there's not much of a profit versus a profit of like coal or fuel and other things.
So, and what
Is
I,
that a counter to your argument you just gave?
So, but
It's the problem.
why would they put it in there if it's not as a profit? 'Cause
so my answer to that would be that, okay, when you buy so we're probably running out of time, but if you buy a bottle of pop, what do you pay for in British Columbia? You pay for the bottle, you pay for the pop, and you also pay this deposit that you get back if you return the bottle, right? So in BC, we have this, for certain goods, when we buy them, we're paying for the disposal in advance.
Batteries and stuff like that.
Batteries, yeah. So, and that's more and more the case.
Yeah.
Tires. So I think that it only makes sense that we pay for the cost of, like, the environmental cost for products. And if we were to pay for the environmental cost of oil and coal, for example, they would be a lot more expensive. But what instead what happens is, in countries like Canada, is we heavily subsidize the oil industry. We give them huge tax breaks. And whenever there's an oil spill or the environmental disaster, who ends up on the hook for it? It's the taxpayers. So all over the place, we're giving these companies tax breaks, and we're basically giving them money, and we're doing the cleanup, which is kind of, I don't know. To me, if you want to talk about, like, essentially what you're saying is you like the market, the free market, to kind of dictate things.
Yeah.
And if you're going to do that, I think the way you do that is by putting the market price on dirty sources of energy. That's one way. I don't know. I'm not an economist, so don't quote me on that. When we read our.
I think the important thing for Frida, though, is, and I thank you for raising all of these questions. He's not the only one who had questions, but he's been bold enough, and confident enough to raise them. So I appreciate that, because otherwise, why did you come? If all we have is an exchange of cliches, then there's no point having this meeting. So don't feel at all worried about raising these questions. But I think that our guest has clearly separated the science out from the technology. These are pictures of technological ways of meeting scientific warnings. So it is confusing when you say on one hand, wait a minute, they're doing this thing for profit, and then in this very same breath almost, to say, and there's no money in it. His answer to both, and let me make this point here very clearly, with eye contact, is his point was that science is not interested in profit or loss. And I think you're struggling with accepting that.
Yeah, like this has nothing to do.
Themselves, if they're looking at it from a business point, they don't make money, but the scientists and the people investing in the scientists, the scientists make money.
Okay, I just said, he said twice, I said 3 times, his argument is scientists get nothing out of it.
Yeah, so this picture, this is just like one way we might try to deal with the science, but all this other stuff has nothing to do with the technology.
I want to dwell on this for a moment, though, James, because Frida speaks for a lot of people who feel that, well, first of all, as free enterprisers, they don't believe that there is much motivation beyond profit. I mean, that's a good human motivation. I mean, saints and Lady Teresa and so on might give their lives over to something, but the average guy doesn't do that.
Yeah.
It turns out that the argument is that people, I mean, all right, you could make $1 billion, you and he together, if you came out with a scientifically supported argument that there's no global warming, because the paradigm is that there is global warming. Okay? But James's point here is that he's a happy guy. He's getting a PhD in an area that he loves. There are professors working in laboratories at universities who make a decent income. Canada's professors, we learned this month, are the highest paid as a group of professors on the planet. It's a nice living. But they don't make more or less money as a professor for saying yay or nay to global warming. And it's important for you to understand. I know you don't want to accept that because you feel that your model is such that they must be lying because it makes money for them. And the counter argument is, well, Professor X and Professor Y and Professor whole alphabet doesn't make a dime more for saying one thing or the other. The only guy who's going to make a dime here is the guy who comes up with a new paradigm.
Are you thinking that they get grants for this sort of stuff? Like money's thrown at them to prove this? Is that what you're trying to say, as opposed to their regular salary?
Well,
Is that what you think?
Let's say so, yeah.
It would be a good argument. The problem here, though, is that most of the grants would come from companies dedicated to finding that there's no global warming,
Yeah.
other than that there is. Because the grants come from Imperial Oil or from whatever it is.
So they're not going to the scientists.
No.
Yeah, so, but in terms of like federal government funding, so let's say you and I had a research lab together and we were going to apply for funding from the federal government. Probably would be NSERC, so the National Science and Engineering Research Council. We would have to come up with a new idea. It would be kind of like peer reviewed the way a journal paper is. So we'd come with our proposal. We'd say this is what we want to do. This is how much money we need, and we'd have to do something new. We can't just do something that's already been done. And the government, I mean, it's the federal government, and our governments are more and more becoming industry focused. So even though it's taxpayer dollars, they would much rather you and I partner with industry. So it's super, super competitive to get these things that are purely funded by the taxpayer now. And we'd have to have a really great idea. And if we're just going to do what everyone else has done and show the same thing that everyone else has shown, the odds are we wouldn't get any funding. So that's, I think, kind of a myth. And in terms of like professors and funding, so I was looking at this job posting the other day. So apparently somebody with my math background, I learned, if let's say I finish my PhD next year, as I hope to, I could go work on Wall Street for some finance company and make $300,000 US a year. Starting salary. It's disgusting.
It's not disgusting.
Well, it's beautiful.
It's beautiful. It's music in his ears.
It's beautiful, but I would be helping the banks make rich people richer. So there'd probably be a little bit of an ugly side to it. Or I can just like fight and claw and try to somehow become a professor, which is super competitive, and I wouldn't make anywhere near that.
And on a parallel issue, guys, just yesterday, I watched a KCND, what's the public channel?
KCTS.
Okay, I watched the show on there with my wife concerning the economic crisis in 2008, the collapse of Wall Street. And this is a parallel issue. It's not about global warming, but it answers your question, which is if X is true, why do we push Y? When X is clearly, that was your question. Well, in this program about the collapse of Wall Street, there are these derivative things that are mostly to do with mortgages that you've probably heard of that are absolutely hollow. There's not a dime in it except selling them. They're totally hollow. At trillions of dollars a day being traded by these companies that were so-called too big to fail. A phrase we now are watching out for. But anyway, the parallel point is that there were people within the organization who were interviewed in this program who predicted this years ago. They said, this is the end of the world. This is global warming in the financial market. This is going to explode and we're all going to die, financially speaking. They kept saying it over and over and over again. And my question watching this was, why isn't anybody listening? And of course, what happened at the end was that we've had this now 5 years of recession, almost as bad as the 30s, because nobody would listen to exactly what caused it. So I would just use that as a parallel, and in the theory of knowledge class, it is a wonderful question about why we humans, we look at 4 ways of knowing, James: emotion, reason, language, and
perception.
What? Perception. And clearly reason, which we humans since the Enlightenment think dominates our approach to life, loses time and time again to things like emotion and self-interest and other things that don't seem reasonable. And that's very much at play here, I think.
Someone asked this of me, so I don't know how to respond, so I'm going to ask you. They said it was the opposite correlation, that because of higher temperatures, there was increased levels of CO2. Like, they said that one was, instead of global temperatures being dependent of CO2 levels, that temperatures were independent and then CO2 levels were dependent of global temperature.
Yeah, so that's a criticism that people have raised in terms of the this curve that I had here, where we had CO2 and average Earth temperature, so the black and the red. So Some of this data suggests that temperature follows CO2, and some suggest that CO2 follows temperature. But this data, when you're going back hundreds of thousands of years, it's kind of hard to get it perfectly in sync. But in either case, I think that the consensus on that, so this is not my area of expertise, but from what I understand is that a warming is that they go together regardless. And so I think some models suggest that a warming planet would also produce a bit more CO2 as well. And so it's really it's hard to say that
One causing the other?
they're linked. And so it kind of doesn't matter if one leads the other. It's kind of the same fundamental processes at play, I think. Question?
Now, on that graph, about 140,000 years ago, there's another big temperature spike. I was just wondering what occurred there. It was kind of that.
End of the Ice Age?
Yeah, I think it's the end of an ice age. So I think that's so on that type of time scale, then big changes like that would be linked to solar changes in the solar input. So the solar input is variable, but only over really large time scales. And so the kind of time scale that we're talking about, way over here, the solar variability just isn't big.
Earlier I saw on your slide about how no new technology is needed. I remember reading a while back about Richard Branson and his some sort of plan to get innovators to create a way to get all the gases in the atmosphere, get them out of the atmosphere.
Yeah.
It's really controversial. From what I hear, what do you think of it?
Yeah, so I think that's I think that those are interesting ideas, but they're also a little bit dangerous. So here's my analogy. Okay, so first of all, the idea is what kind of technological ways could we dream up in order to remove greenhouse gases from the atmosphere? It's an interesting idea because then we wouldn't have to change the existing structure of our economy and our fossil fuel source and all of this kind of stuff. But the analogy that I would use is the following. Let's say that you're smoking. You're a chain smoker, and you're showing early signs that you might be getting some kind of lung problems. So you kind of expect that you're going to eventually probably get lung cancer if you keep smoking. So what you could do is you could quit smoking. Or you could say, well, wouldn't it be really cool if scientists could find some way of getting all this stuff out of my lungs? And I'm sure there's probably a way they could just clean all the stuff out of my lungs, and I'm just gonna wait for that to happen. So that's kind of why I think it's a bad idea. It might work, but it's also dangerous. So it's dangerous in that it's inaction. It's another reason why we shouldn't act, right? And it's also dangerous because we've already shown just how bad we are at messing with the planet. Now, if we had come up with some scheme to try to change something else in the planetary dynamics, like we don't know which, the balance is really delicate, and we wouldn't want to screw things up, the other way either.
You mentioned at the beginning of your speech, I think I've got the numbers right, but I'm sure you'll correct me. 5.6 billion tons of CO2 a year?
Yeah, I think it might be more now.
It was the first one you put up there.
2.6.
Was it 2.6? 2.6?
Where is that? Oh, it's on the carbon side. Yeah, here.
Oh, there it is.
Yeah.
Yeah, let me exaggerate.
2.6 billion.
Okay, 2.6 billion metric tons of carbon in the atmosphere a year. How many metric tons, if we know, is the atmosphere?
Yeah. What does this represent?
Yeah, I think that's. I really probably should have worded that in a different way. Well, the atmosphere is. Yeah, I don't even know. I mean, it's massive, and it's massive, and that. So a common thing that you'll see that people that try to sort of fight these scientific arguments will say is something like, well, the CO2 that we've put into the atmosphere is only like 0.0001% or whatever of the atmosphere. It's some really small number.
Is it? Okay.
Yeah. Like the atmosphere is huge, and when you talk about, I think we're still under 400 parts per million CO2. So 398. 398, yeah. So that's parts per million. So
Okay.
that's we're really talking about well under 1% of.
All right, that's what I was
Yeah.
asking.
So that's,
I didn't know.
Yeah.
because sometimes when you read the statistics, they sound enormous, but then when you
Yeah.
put the
Sure.
comparison in, you don't.
Yeah, it's really small. So and I think that's one of the challenges of this whole issue is that essentially what the science tells us is that we should change our actions now so that our children and our grandchildren can have a more habitable planet. And that brings in, since we have the philosopher here, that brings in an important question, which is how important is it to live the good life now for those in the future, and versus how important is it to make sure that everyone who's alive today has a good life. So one of the people that is a guy named Bjorn Lomborg, who wrote this book called The Skeptical Environmentalist. He's a guy who gets quoted a lot in the media, and essentially he's also preaching to this idea of inaction. He says, well, malaria and poverty in Africa is claiming all of these lives. So we should really worry about Africa, and we shouldn't worry about climate change. And that's, it's really just it's a philosophical question, because how important, is it more important to save children that are alive today, or all of the children that will be alive in 100 years? And that's not really for science to determine.
And,
So-
the concept that my students will immediately think of is the law of the excluded middle. You've given us an either or, and we know that we could do both.
Mhm.
Because philosophically we should not exclude the middle, but we do. In
Yeah.
other words, if we save the planet, we're not going to save any Africans.
Yeah.
Can't you do both?
Yes.
On the topic of educating people about global warming, there's a lot of disinformation at the current point in time from what I've seen. I remember in my grade 7 classroom we had a teacher who basically told us, oh, well, in the winter in my shed outside, my bottles of wine froze and the glass burst. So really, if we have icebergs that are melting, wouldn't we have much less water in the oceans? And everyone in the class was like, yeah, that makes sense. And there's a lot of disinformation going on. How do you think we should be focusing on effectively getting this across to people?
Yeah, I think that's a good question. Well, I think that one thing that I've heard people say, and I've read, and I kind of agree with, and then I broke that rule by coming here, is people say you should never engage in a debate on the science of global warming, because it's like, as I hope I showed you, there's really no debate about that. I mean, there's a lot of debate about what we should do, right? But the science strongly suggests something, and you can't really find, credible scientists that would.
Mr. Cliff, please call the office. Mr. Cliff, please call the office. Thank you.
So the recommended approach is don't debate the science. I mean, it's all on the internet. You can read about it. It's all in the published journals. There is a consensus. Number one. Number two, I think that there's too much of this rhetoric of like scare tactics, like the Earth's going to be underwater. There's going to be Hurricane Katrina's all over the place.
No fish.
No fish. Well, there's going to be no fish because we're overfishing the ocean, so that's a completely different topic. So I think the scare tactics are not helpful. So I think that's another thing. And a third thing is that really, I think I think the kind of changes that we need to make are things that are only going to make our community stronger anyway. Like, who wants to be driving all over the place all the time? Wouldn't it be nice to live in a place where everything was closer and you could walk? Who wants to get all of their produce shipped from the other side of the world? Wouldn't it be nice if you lived in a place where you ate more local produce? Wouldn't that be good?
What if you wanted to eat pineapples?
If you want to, well, so there are certain things that that it's a little more challenging, like pineapples. It's true.
And there's the question of need and want.
Yeah. My wants or needs.
Well, listen, if everybody had the same needs/wants as you in the whole planet, then there just wouldn't be enough pineapples for everybody, right?
Then there won't be enough space for all meat.
Yeah, so I mean, these are, I kind of think that the way we want our lives to be anyway would be, less pollution, cleaner cities, more, I guess, fresh air, more sense of a community. These are all things
You made
that...
it pretty clear this is James the citizen speaking now, not James the scientist.
Yeah.
That's clear.
Yeah, that's true. That's true. So the stuff that I, as a scientist, I've already said my science way. I'm just trying to kind of inform the debate about, what do we do about it.
I'd like to thank you for coming, James. I think this has been great. I'm not saying you have to stop now. I'm just saying I think we should point out that we're grateful you're here.
I'm glad to be here. If you guys ever have any future questions, I can leave you my email. Actually, you've got my email. You could circulate it with the students. You can always email me, even if you want to attack me with more questions about how I'm going to make millions on my solar cells. These are important questions, and I don't have all the answers. But one thing that actually we were talking about after lunch is that one thing that I've noticed, that we've both noticed, I think, in society, is that we have all the time these critical issues that are central to going forward together as a society, and we don't talk about them enough. We don't discuss the opposing viewpoints enough. There are too many crazy environmentalists who only want to talk to each other about how evil all the oil companies are. And there are too many pro-tar sands people who say anyone who's against the tar sands is unpatriotic and is just a dirty, crazy hippie. Unfortunately, there are lots of both of those people in the country, and we all need to sit down and work through these things together. So
the truth.
Instead of those monologues, we need some genuine dialogue.
Yeah, there needs to be some, I think the environmentalists have to soften a little bit and give in a little bit to industry, but industry also has a lot to compromise on too. So I encourage you to help fight for those compromises in the future.
Yeah, good point.
Thank you. Any more questions? You're welcome to ask them if you do. I'm not rushing it. I thought we were kind of winding down. No? Good. Thanks.
More about the...
Margie's got a question.
Specifically the Kyoto Accord, you mentioned that it would have been ineffective in how it would have addressed the issue. What do you think is an idealistic solution to getting rid of global warming? Do you think that completely cutting, to what extent do carbon emissions have to be cut to remove the issue that we're currently faced with?
Well, one of the challenges is that, so the Earth as a system is really, the Earth is quite adaptable, but it takes a long time to adapt to things. And one of the things about the greenhouse effect is that eventually the Earth will reach an equilibrium where if we stop producing if let's say we turn off all sources of greenhouse gas emissions tomorrow, well, CO2 stays in the atmosphere for, I think it's thousands of years. So we're basically, even if we don't emit any more greenhouse gases, it's going to take still another, 50 or 100 years maybe for the Earth to adapt. In other words, it'll still keep warming. Yeah, so it'll keep warming no matter, even if we don't produce any more greenhouse gases. So it's kind of hard to talk about exactly the level we need to be at, but it'd be nice if we could stabilize things at some constant level. I think there are some, I don't know exactly what the latest projections are, but there are some people that say we need to do certain measures over the next 50 years, and then we can stabilize things at just a 2-degree increase, which is still quite a bit for the planet, but there are things that we could do. But I think it's really hard to talk about agreements like Kyoto, because Kyoto says, we all have to cut our emissions to is it 20% below 1990 levels or something? By 2012, I think.
No, this year.
Yeah. So I think those agreements are hard because it's hard to enforce all that stuff. Everyone has to sign on. If one country doesn't sign on, it's a problem. So I think it's better to just think in terms of do what you can in your own place. So for example, in the EU, I think Germany, England, and France have all started reducing their greenhouse gas emissions by quite a bit. So the EU is kind of leading the charge, and Canada and the United States are like, we're the big offenders.
Have you seen the documentary, The Great Global Warming Swindle?
I've seen parts of it.
Have you? And they're talking about the part. I was talking about the part how, since we have to cut all our emissions, how do third world countries develop, and aren't we just holding them back?
Well, it's interesting that you say that. So I have a friend who worked in Ghana for a while, and then he worked in Vanuatu in the South Pacific. And I mentioned something like this to him once. I was saying, you know, this is unfair. You know, the children in these developing countries are going to be the hardest hit. But he said something really interesting that I didn't expect, which is that actually, in a lot of these developing countries, they already live a low carbon lifestyle. So, for example, in the island, one of the islands in Vanuatu where he lived, they already have wind turbines, and they have so they don't have like street lights the way we do, but they have these rechargeable battery flashlights that everyone has, and I think they're like solar cell flashlights. So even though they're like kind of a primitive economy in some ways, in other ways, because they don't have such like large energy overheads, they don't have like
infrastructure.
Yeah, they don't have the infrastructure that eats up all of that energy. So in some ways, these developing countries, they have the chance to kind of do it right now. They can plan their cities as they expand, as they become a bit more industrialized. They can plan them in ways that are more sustainable.
The only problem though is that costs a lot of money.
It doesn't have to.
What would cost a lot?
Yeah, what part of it costs a lot of money?
Well, green technologies, wind things, solar panels, they cost a lot.
Go ahead, Rosa.
But I think the problem that it costs a lot of money for us now is that we already have our structure, and then we have this dependence, and then we have to cut that off and start from the beginning. And we have a large population to support from the very beginning. So it can't be a small scale. It's a humongous large scale project that you have to start by wasting all the money that we've already spent and then starting from scratch. That's why it costs money. But if you start from the beginning and from the right place, then you shouldn't. It actually would cost a humongous amount of money to have all the electrical systems, wires, the street lights, that they don't have this kind of infrastructure. And if you were to have the traditional coal mining or even our hydroelectricity system down in, I don't know, Ghana, some South American country, you don't know, it would actually cost just as much money or maybe even more because they don't have these systems already.
That was my point. Yeah. Well said.
So now that we know that the third world countries are not the problem, how do we plan for the transition into green energy? How do we get away from all this coal burning and all the big companies who's holding all the shares? How do you get away from that?
Well, that's the hard part, is that I think in our country, and like most democracies, it seems that the special interest groups are really powerful. And a lot of the decisions that, unless we really come together as people and demand something, then typically the big companies kind of.
But even if you demand for drastic change, that's also going to affect us negatively as well, since our economy is so dependent on those.
Well, it's going to change things, but it doesn't have to be totally bad. So, for example, we know. So let's imagine that we're going to. What's your name? Min. Let's say we're going to go into business. Okay.
Yeah.
We'll call it Min James, putting you first, Min James Industries. So at Min James, so MJI. At MJI, let's say we're going to go crazy on green technology, okay? Canada has a lot of really well-educated people. And if we became like the industry leaders, if as a country we decide we are going to be the green technology country, then okay, there's going to be like initial startup money that we're going to need, but I think the whole world is going to want that technology. Like oil is getting more and more expensive all the time, and the only reason the tar sands are even a viable option is because we're kind of running out of oil, right? So if we can produce these green technology and we can make it more efficient, and we can do it at a larger scale and make it cheaper, then it becomes something that people want.
But I don't think the oil companies are just going to let it go like that. even if they don't have oil, I'm pretty sure they'll.
Alina Tayo, could you come to the main office, please? Alina Tayo, could you come to the main office? Thank you.
And Min, the impracticality of the truth doesn't make it less true.
Yeah, but I'm just saying, so I'm sure they won't be happy to give up control.
No, they won't.
So like what could happen too is they can take control of that green technology since we are such a, even though my ideas and your ideas are the best and we have this passion and people are excited, I think like the main difference is that they will have the power, the money to actually like dominate, like monopolize this market, like this new market too, and then they can control the prices from there.
Yeah, if they want to compete with us, but if we have products that they don't, then they can't really compete with us. The only way they can compete with us is if they are better than us at green technology, which is.
I can see ICE having another guest speaker coming in from industry to talk about the issue of whether accepting the truth about climate change can lead to practical industrial solutions. How would you like that? How would you like me to do that?
Yeah.
Sure. I'll do it.
We should have a
Look at the other
tradition
side.
of semi-TED Talks.
I'll get somebody. I got
Go! Semi-talks.
semi-tops. There we go. Because James, you're being put on the spot here. It's not a spot of your
It's
creating.
not my deal. But you know what? I'm sure there are people like.
Oh, there will be.
I can help.
I'll find it.
Yeah.
Found you, man.
Yeah, that's right. Yeah.
Okay, thanks, guys. You're free to go.
Semi-talks.